For our first problem, we have an indoor physical fitness room that consists of a rectangular region with a semicircle on each end. The perimeter of the room is to be a 200-meter single lane running track. So part A is just draw a diagram that illustrates the situation. So we have this rectangular region, and it says there's a semicircle on each end, assuming that's the narrow end. Something like that. Let x and y represent the length and width of the rectangular region respectively. So length I consider to be the longer dimension, width I consider to be the shorter, although it doesn't technically matter. So that's it for part A. Then part B says determine the radius of the semicircular ends of the track. So the radius is from the center to the edge of the circle, so that's y divided by 2, or 1/2 y. Then also determine the distance in terms of y, meaning y should be our variable, around the inside edge of the two semicircular parts of the track. So figure out this distance and this distance. So if I put two semicircle distances together, I get a full circle. And the distance around a circle is circumference. And the formula for circumference is 2 pi r, or it's also pi times diameter. Either way. Since we have r, I'll do 2 pi r. So that makes the circumference 2 times pi. We want a function of y, not a function of r. So substitute y divided by 2 and for r. So the distance around the two semicircular parts, 2's cancel. It's going to be pi times y. So here are the two answers for B. For part C, use the result from part B to write an equation in terms of x and y, so we'll have both variables, for the distance traveled in one lap around the track, and then solve that for y. So we have the distance around the semicircular part already. So we've got pi times y, and if we add to that x plus x, 2x, we know that, remember here, we have 200 meters. So this equation should be equal to 200. So this is a perimeter equation of this shape here. And then it says solve this for y. So you would subtract 2x. That'd be pi times y equals this. So divide the whole thing by pi. So there's our equation solved for y. And I want to throw in an extra piece. We need to get used to, for just as good practice in mathematics and in preparation for our AP test, we need to get into the habit of figuring out perimeter. So think about this value, the x values that we can plug in. We only have 200 meters to work with, so x certainly can't be 200, and x definitely can't be 0, because then there wouldn't be a track here. But it's not 0 to 200. That's our domain. We will say x needs to stay greater than 0. We have that much. But we need this y expression. We don't want y to equal 0 either, right? X can't equal 0, y can't equal 0. So y needs to stay positive. We want to make sure y stays greater than 0 as well. Make a list here instead of writing it backwards like that. Okay, x needs to stay greater than 0, y needs to stay greater than 0. Well, what's going to make sure y stays greater than 0? If 200 minus 2x over pi stays greater than 0. The pi doesn't matter here. You can multiply pi to the other side. And solve this for x. So as long as 100 is greater than x, or flip that around, as long as x is less than 100 but bigger than 0, so as long as x stays between 0 and 100, this function is viable. Otherwise, if you're outside of those dimensions, then you have negative dimensions, and that doesn't work. So they don't require us to do this, but this is good to think about, again, just for these higher level mathematics courses that you're in now and for our AP test. use the result from part C to write the area of the rectangular region as a function of x. So we don't care about the semicircles. The area of the rectangle, just before I get into it, is x times y, length times width. We want this as a function of x, so that means keep the x, substitute the y. So a of x is equal to x times, our expression for y was 200 minus 2x over pi. And you can distribute the x through or not. The domain is still the same. X can't be 0, and it can't be anything 100 or larger, so it's got to stay between. And then part E says use a graphing utility to graph the area function from part D. Use the graph to approximate the dimensions that will give a maximum area. So let's type this into our graphing calculator. I think I'm just going to distribute the x through. So 200, oh, sorry. I need parentheses around the numerator. 200x minus 2x squared. And then that's getting divided by pi. Always use the pi symbol, not the approximated 3.14. And then remember, another reason that it's good to know about domain is because it makes the calculator graphing portion easier. You're not just guessing and checking. We said x should go from 0 to 100. I don't care if it counts by ones or not. And then I'm going to zoom fit, which is option 0. So I'm just going to press 0. And remember, what that does is it holds your domain and it figures out the y values for you. So you don't have to go through and guess and check and guess and check. And then we're supposed to find the maximum. So second trace, maximum, go to the left of the vertex, go to the right of the vertex, and press enter a third time. So this rounds up to 50. And I would just leave either round to 3 places for the area, or I guess it just asks for dimensions. So E is maximum area when x equals 50. And what are we talking about? Meters, 50 meters. And remember, you need to solve for y. So y will equal 200 minus 2 times 50 divided by pi. So let's just leave our answer exact. 200 minus 100 is 100 divided by pi. There's really no reason to type that in and see what that approximates to. I would just leave my dimensions like that. Oh, and here's a screenshot of what I typed in. Okay, for the next problem, a child care center has 200 feet of fencing. Fencing is always perimeter to enclose 2 adjacent rectangular safe play areas. See the figure. I drew the figure again, just sort of bird's eye view. There are 3 of these y dimensions and 4 of these x dimensions, the way that they labeled it. Part A, write the total area of the play areas as a function of x. 2 ways to look at this, I guess. There's one big rectangle. It doesn't matter that we have a y cutting down the middle. So the total area is 2x times y. Or you could say add the area of the left side to the area of the right side. X times y plus x times y is still 2x times y. So let's start there. The area is 2x times y. This says write the area as a function of x. That means we can only have x. We need to substitute out this y. And this is where the amount of fencing comes in. So remember, fencing is a perimeter equation. So 200 feet of fencing is going to be along the 4x plus 3y lines. So all that has to add up to 200. And then we're trying to substitute the y in the area equation. So solve this equation for y. Subtract 4x, divide the whole thing by 3. And then that gets substituted in to the area equation. So area as a function of x, a of x, is equal to 2x times 200 minus 4x over 3. And then it might be easier if you're trying to figure out domain and range again. You can either do the same thing I did, say, okay, x needs to be greater than 0, y needs to be greater than 0. What's going to make the y greater than 0 if 200 minus 4x over 3 is greater than 0? And get the 3 out of there. Solve for x. You can do that, or I think in my answer key that I posted, I might have, just to make this look nicer, I noticed I could factor a 4 out of 200 minus 4x. So if I factor a 4 out, 4 times 2x is 8x. This becomes 50 minus x, whole thing's over 3. So here it's a little more clear too that x needs to be bigger than 0 and less than 50, but it doesn't matter how you simplify it, how much you simplify it. I'm mostly interested that you get the correct domain. And again, why do we go through all the trouble of domain when it doesn't really ask for that? Like if you check the answers in the back of the book, it doesn't list a domain, but it's important for parts B and C. If I want to use my graphing calculator quickly and effectively for homework, on a test or a quiz in here, on the AP exam, knowing the domain is like half the battle to graphing it quickly. So B says use the table feature to approximate the maximum area, or the dimensions that will give maximum area. C is use the graphing utility. So I'm going to do B and C kind of at the same time. First I need to type in this equation. So it was 8x times, what was it? 50 minus x divided by 3. All right, change the window to 0 to 50. Zoom fit again. So here's our new parabola. Because I'm on the screen, I'm just going to use the graphing feature. Also, if I have my graphing calculator, I'm not going to use the table to try to find a maximum. I would just use this feature. It's good to practice that in case the AP exam gives you a table rather than the function to type in. Okay, so this is showing me that, and I've got a screenshot of this, if the x dimension is 25, oops, I just wrote 52. If the x dimension is 25 feet, we'll get a max area. Remember, this y is not the y dimension. This is really the area. This is a of x. So when y is 25, you've got to go back and plug that in. Or when x is 25, go back and plug that in for y. So y would be 200 minus 4 times 25. So 200 minus 100 is 100 over 3 feet. If you go to table, so I want to remind you of this. Second graph will take you to a table. Now mine's in the 20s because I did these problems before, but if you're back here at 0, and you don't want to scroll all the way down to 20, it's going to be or 25, it's going to be halfway between 0 and 50. You can go to second window and tell the table where to start. So maybe you're guessing, you're not sure that it's at 25, so you say you start at 20, and then you press second graph, and it'll hop there, and then you have less scrolling to do. So that's nice. If they give you multiple choice answers for an AP test, you can just jump around to each value. Second window, tell it to start wherever, and then second graph to see what that corresponding point is. The largest area was again at x equals 25 feet and y equals 100 over 3 if we plug back 25. And then part D says, this is kind of interesting, write the area function in standard form. Remember, standard form is vertex form. To algebraically find the dimensions that will produce the maximum area enclosed. So again, this is just like a third way. You can look at things on a table, on a graph, or from the equation. Now, I don't really want to complete the square on this area function. I'm going to use the vertex formula and then just write it in standard form because it doesn't tell me to complete the square. So if I'm not told, I'm not really going to do it by choice. Okay, 8 times 50. So 4 times 50 was 200. So 8 times 50 is 400. X. 8x times negative x is minus 8x squared. Each of those is divided by 3. So if you're going to do the vertex formula, remember you need to have this in general form first. And then the vertex formula says h is the opposite of b divided by 2 times a. And then we're going to fix our fraction divided by a fraction. We're going to take the top fraction and multiply it by the reciprocal. Let's do 2 times negative 8. The reciprocal, the bottom fraction, 3's cancel, negatives cancel. Dividing by 16 is weird, but if I divide by 4, and then I divide again, that's much easier. So that shows me that h is 25. I can find the k value. K is a of 25. Since I'm supposed to get this in standard form, I'm going to go through all this trouble. So back to a of x. 400 times 25 over 3 minus 8 times 25 squared over 3. I'm not doing that math in my head. I'll just hop on over here. They're both over 3. So 400 times 25 minus 8 times 25 squared. Get that answer because I didn't put parentheses around. Oh, and then divide by 3. So I'm just going to leave it as 5,000 over 3, which should be 1,666.6 repeating. Finally, get this into standard form. So remember, you need to keep the a value out in front. And then it's x minus h squared plus k. Find the dimensions for the maximum. Well, I didn't really need to rewrite this form. I found the dimensions back here. H represents x, so x is 25 again. Y would be 100 over 3. And part E says, compare your results from parts B, C, and E. So I'm just going to say they are the same. They all say, whether it's a table, a graph, or an equation, they all say that x equals 25. I should use equals. X equals 25 feet. Y equals 100 over 3 feet. Those are the dimensions for max area. Okay, next problem, height of a projectile. The height y in feet of a punted football is approximated by this model. X is the horizontal distance, also in feet, from where the football is punted. See the figure. So this doesn't give me an obvious domain to start out with. So it just says use a graphing utility to graph the path of the football. So let me just take you through my thought process here. First, type the thing in. Negative 16 over 2,025 x squared plus 9 over 5 times x plus 3 over 2. Now, if you just zoom 6 standard to see what happens, that's not what we want. We want the full path. So let's go to window. The x minimum should definitely be 0 because that's where it's getting punted from. And then I don't know how many feet do we think someone can punt something? Like a football field is 100 yards, right? We're talking about feet though. So I don't think you could punt across a whole football field, but I could probably say, let's just go 300 feet, see what happens. So that should be long enough. It might be too long, but I'll just go 0 to 300, and then I'll just say zoom fit from there. Okay, so that's pretty good. I just need to be able to see the path. You can see this window I have here is different from whatever I set up here. I don't remember what this was. And that's okay. So, okay, you've got some sort of graph here, check. And then how high is the football when it's punted? So they give you this hint, although you should be able to figure out when it's punted, this is the same as the initial point. So find y of 0. And no calculator or graph is needed for that. If you plug in 0 for x, you get 3 over 2. We're talking about feet, or 1.5 feet from when it's punted. Part C, what is the maximum height of the ball? So I've got my screenshot there, but remember if you can see the vertex, you just do second trace, maximum, move to the left of the vertex and press enter, move to the right of the vertex and press enter, guess, press enter. The question was, what's the max height? So that's the y value. So I've got it right here. So the max height is about 104.10, oh, sorry, 0.01 and this is feet. Part D says, how far from the punter does the football strike the ground? So here, or on my graph here, where does the football hit the ground? That's asking you to find the 0. When is y equal to 0? Now, you could do quadratic formula. You've got a calculator, you could do quadratic formula. But if you've got the thing graphed already, it's much faster to say, find the 0. So second trace, find a 0. Our goal in mathematics is to be efficient and accurate. You don't want to always do things the long way just because you've memorized one way to do things. So yeah, we could use quadratic formula, but so much faster just to do this. And we're much less likely to make a mistake this way. So the x value is that horizontal distance. It's 228.643. So I'll just say something like strikes ground 228.643 feet from punter. Okay, we have another path for 62. The path of a diver is approximated by this function, where y is the height in feet and x is the horizontal distance in feet from the end of the diving board, and they've got a picture for us. Now this one doesn't tell us specifically to graph, it just says what's the max height. So I could graph this, but I think it would also be just as fast to use my vertex formula, right? The max height is whatever hk is, because this is quadratic. So I'm still going to use my calculator, but I can say h is the opposite of b over 2a. Maybe I don't even need a calculator. Look at this. Flip this around. Instead of divided by -8/9, it's times 9 over -8. 9's cancel. -24 over -8 is 3. The question is not how far. So now I know this is 3 feet out. What's the height? The height is k, which is y of 3. Let's see. Squaring 3, you get 9. It's good to practice this without a calculator. Again, you could probably use one, but this would be fair game for no calculator because the numbers are so nice. 9's cancel. 3 over 9 is 1/3. 24 over 3 is +8 plus 12. Yeah, so k is 4 plus 12, 16 feet. That's our max height. All right, next problem. You have a steel wire that's 100 inches long. To make a sign holder, you bend the wire x inches from each end to form 2 right angles. So that's why this dimension is now 100 minus 2x. To use the sign holder, you insert each end 6 inches into the ground. So now these x's on the sides became x minus 6. Write a function for the rectangular area A enclosed by the sign in terms of x. So I don't have any y dimensions here. A of x is just length times width. So in any order, 100 minus 2x times x minus 6. I would not bother distributing that or figuring out like what its general form is. I would just leave it like that. I do want to think about domain again. So neither of these dimensions can be 0 and neither can be negative. So we need 100 minus 2x to stay greater than 0, and we need x minus 6 to stay greater than 0. Because we're talking about dimensions of something, we can't have negative dimensions. So x needs to stay less than 50, but bigger than 6. So 6 to 50 is our domain. That's going to help me for part B. This says use the table feature to determine the value that maximizes the rectangular area. So if your domain is 6 to 50, if you want to graph this thing, you can. But just know that like somewhere halfway-ish between 6 and 50 is going to be the maximum. So I'm going to type this in. So it was 100 minus 2x times x minus 6. So I'm going to go to table set and tell the table to start at like 25 and then second graph. And I'm just looking for the highest area. So it looks like it's right here. At 28, we get 968. So we're using that table to say, it looks like, yeah, about 28 inches. All right, next problem. I have a little bit of a discrepancy with what the textbook says the answers are for part A and the way they worded their problem. And it's important for our AP exam and just for accuracy in general. So let's read through this. The monthly revenue R in thousands of dollars from the sales of a digital picture frame is given by this function. P is the price per unit in dollars. Part A is just find monthly revenues for 50, 70, and 90. So we're just plugging in or evaluating the function at each of those values. But remember, when we find R, when we've done this with regression equations before, if R comes out to like, say, 5, and this says thousands of dollars, that's not $5 then, that's $5,000. So let's go ahead and calculate this and see what R comes out to. So negative 10 times 50 squared plus 1,580 times 50. So I get an answer that's in the thousands. Now, the textbook showed me that 54,000 was the answer. They said $54,000 done. And I'm not sure if that was a typo or not, but the way that this problem is worded, it should be 54,000, which sounds silly to say 1,000, 1,000,000 is a million. So what you can do to make this look better is just take your answer and multiply it by 1,000, which would tag on another 3 zeros. And then you don't include the word thousand at the end. So either this is the answer or you just make it millions. The textbook did not include the thousand, and I think that that's wrong based on, now 54 million sounds like a huge monthly revenue. I just think they mislabeled the problem, but I want you to get in the habit of paying attention to that. So we're going to call it 54 million. Okay, and then we're switching out the 50s for 70s. So remember, you can go up here and press enter and then just type over the 50s and make them 70s. So again, I'm going to make this 61,600, and then I'm going to multiply it by 1,000 and put a dollar sign in front. So 61,600,000. And then if you don't have a graphing calculator, like a newer one that allows you to come up here and grab this, you can also just press second enter and it will retype your last line. And then you can go over and edit. So we want these to be 90s instead of 70s. 61,200, and then multiply it by 1,000. So we're saying that this digital picture frame company, this is probably wrong, has $1 million monthly revenues. Again, I think if they just would have taken off the in thousands of dollars, it would have been fine. But I'm leaving it in, so this company's business is booming. And then part B says, find the unit price that will yield a maximum revenue. So P is the unit price. And then, so basically this is saying for the vertex, find H. And then part C is saying, what is the maximum monthly revenue? So that's figure out K. So I don't have this graphed, so I'm going to go back to my formula again. The opposite of B, the opposite of B over 2 times A. So 1580 divided by 20 is 79. So when P equals $79, this is the price per unit. That's when we get a maximum revenue. And then what is the maximum revenue? To figure out K, you plug in H. So evaluate R of 79. Again, you can either press second enter until you get that last line, or if your calculator allows you to go up and grab a previous line, then do that. Change the 90s to 79s. And we get 62,410. And we're going to multiply that by 1,000 because revenues are in thousands of dollars. Okay. Next one is about cigarettes. So for selected years from 1955 through 2016, the annual per capita consumption C of cigarettes by Americans 18 and older can be modeled by this function. They give us a domain. T equals 5 is 1955. Okay, so use a graphing utility to graph the model. So to get this graph, I into y equals typed in the equation, negative 1.08 x squared plus 19.2 times x plus 4,048. And then they give you a domain. So in your window, make x min 5, x max 66, and then zoom fit, which is zoom 0. And I got that window. Okay, so graph it, done. Use the graph to approximate the year when the maximum annual per capita consumption of cigarettes occurred, and then approximate that maximum. So find the maximum. It looks like the vertex is up here somewhere. Makes sense. It's like earlier in the 50s. So we're going to find the maximum. This takes my cursor a long time on the computer to get over there. Remember to move a bit to the left. So I'm not sure, that looks like a flat line. So I'm going to go pretty far left and press enter. And then I'm going to try to get past that like flat line. Press enter and then have it guess. So I'm getting this value here. So we want the year and the maximum consumption. Just split so I don't have to keep going back and forth. So I'm going to say now this is years, 5 is 1955, so this is years after 1950. So this is during or toward the end of 1958. The maximum, I'm just going to call it consumption, was 4,133.333 cigarettes. I guess I should say was about that many cigarettes. I guess you could argue that you could consume a third of a cigarette maybe, but won't get into that. And then the last thing says, beginning in 1966, all cigarette packages were required by law to carry a health warning. Do you think the warning had any effect? Explain. So short answer, yes. I'm not going to rewrite this, but yes, because we could show where 1966 is if we want to. We could say, go to the value, that's what, 16. Here's 1966. The consumption has already started decreasing, but here and then even after that, it keeps decreasing faster and faster. And I wanted to relate this to concavity because that's a big idea on our pre-calc exam. So we have a decreasing function that's concave down. If you were to draw in little slopes, little secant slopes or average rates of change, they start off negative at 1966 and they keep getting more and more negative. So what that tells you is not only is the consumption decreasing, but it's decreasing at a faster rate each time, as time goes on, right? So it's dropping more and more drastically. So I just made a note of that. This graph is concave down. The function is decreasing. So when it's concave down, we always say, well, that means the average rate of change is decreasing. That sounds like something's slowing down, but again, if you have negative slopes that are decreasing, like maybe this is, I'm totally making up numbers, negative a half, now the slope is 2, negative, now the slope is negative 5, that's getting steeper and steeper and steeper and dropping faster and faster and faster. Okay, next function. The population P of Cuba in thousands. So this is funny because they did this again in thousands, but in the textbook, when I checked my answers, they did multiply their answers by 1,000. So anyway, the population of Cuba in thousands from 2008 to 2018 can be modeled by this. Here's our domain. So 8 corresponds to 2008. According to the model, in what year did Cuba have its greatest population? So find the maximum. Find the year that the maximum happens and what it is. So let's type in this model. Negative 2.61 x squared plus 54.02 times x plus 10,988. Windows should be set from 8 to 18, and then we zoom fit. And then we find the maximum. Second trace, maximum. Get this over to the left. Press enter. Move it to the right. Press enter a third time. Okay, so this is, again, these are years after 2000. So in 2010, toward the beginning of 2010, we had this max population. Now, I Googled this as well, because this one I could actually check. This is like a real thing. The other one, I don't know what the business was to check whether the monthly revenue was accurate or not, but I Googled Cuban population in 2010, and it was not 11,267. That'd be very small. It was multiplied this number by 3, or by 1,000. Move the decimal place 3 places. So it's 11 million people in Cuba at that time, not 11,000. Okay, so in 2010, the max population was about 11,267,517 people. According to the model, what will Cuba's population be in the year 2050? So plug in 50. You can do that by doing, well, you can't do value. Let me check this. I don't think you can do value 50 because 50 is outside of my window. Yeah, but you could, this is in Y1s. You could do alpha trace Y1 of 50, and it will give you that answer. Remember to multiply that by 1,000, but that would mean that the populations only went from 11 million to 7 million. So do we think this is accurate? Do we think it's reasonable? I would say no. The model's accurate for 2008 to 2018, but after that, we wouldn't expect, this is a parabola, we wouldn't expect the population to just keep drastically decreasing, right? So this is I would assume this is not accurate. You could also Google what's the population now and see if it's changed dramatically from 11 million. Okay, these last two problems, I just wanted to remind you how to solve systems. We have not formally done systems of equations, but we have been using substitution this whole time. So these are problems that, I don't know, you'll see stuff like this on the ACT. You'll need to have the skill to solve different applications like we've been doing. So I just wanted to kind of do this real quickly. I'm not going to verify on my graphing utility. I'm just going to solve the system of equations, which means if you were to graph, you'd be finding points of intersection. Now you can use substitution if you want, or this first equation, if you remember how this works, this is set up for elimination. If I just multiply the top equation by -1, and then add the two equations together, -2/3 minus 1 is -5/3 x. The y's cancel out. 6 minus 8 is -2. Solve for x by multiplying by -3/5. So that becomes positive 6/5. And then you've got to solve for y. So if you go back to, I'm going to use the top equation again. X, which is 6/5, plus y is supposed to equal 8. Because I'm going to be subtracting 6/5, I'm going to write 8 as 40/5. So y is 34/5. So our point of intersection as an ordered pair is xy. So 6/5, 34/5. If I were to solve these equations for y and graph them, this should be the point of intersection. And then what if you have a quadratic in a line? So this is where I would say, well, these both are equal to y. I wouldn't necessarily do elimination here, although it's all the same thing, just different formats. I would just, if both of these are equal to y, it means I can set the equations equal to each other. And I'm trying to solve a quadratic equation at this point, so I want to get it equal to 0. I want my x squared to be positive. That's just personal preference there. Means I've got to subtract 9 to this side. This is factorable. So I get two values for x. X equals -3 or +2. That means that I need to calculate two different values for y. So when x is -3, y is -3 plus 3. So -3, 0 is 1 point of intersection. And when x is 2, y is 2 plus 3. So 2, 5. Okay, and one last thing about this. 87 was the intersection of two lines, so I should just have one answer at the most. 88 was the intersection of a parabola and a line, so not that I have to have two answers, but it makes sense that I could get two answers because a parabola and a line could intersect like that. All right, that's it for today. If you have questions on this homework assignment, please come to office hours or ask at the start of class.